Hello everyone, happy to have you here. Yes, well, I'm glad that you guys have decided to join us today for this session, for the very last session of the day. This session, which is on early career researchers' perspectives on data repositories across disciplines, geographies and cultures. It is being jointly organized by CODATA Connect and World Data System. So, before we start the session, we want to give acknowledgement of the country. I would like to begin by acknowledging the traditional owners, the Turrbal Yugera people of the land that we are meeting on today in Brisbane, and pay my respect to their elders, past and present. So, for this session, this is the session overview. We have 5 different speakers, and if you have any questions, any of you, please, we will take the questions towards the end of the session, but yeah, if there's any burning, urgent question, feel free to raise your hand, and if you have time, we will accommodate that. So for the very first speaker for today, I would like to introduce on this stage Dr. Claire Rye, who would be talking about learning from helping to build data repositories, and the floor is yours.
Thank you. Good afternoon. So it's a pleasure to be here. I'm hopefully going to keep this reasonably short, if I can use the, so I'm going to talk from, I guess, a couple of different perspectives. I'm currently at the University of Auckland in Aotearoa, New Zealand, and was previously working at MBIL EBI in the UK. So I'll start off talking about that time with a project called the Human Cell Atlas, which was, I guess, started about 8 years ago, a joint project between the Broad and Sanger Institute in the UK, and really had the ambition, I guess that lofty vision of mapping out, understanding around the 27 trillion or 37 trillion cells in the human body and working out exactly what did what, and using single cell sequencing and expression in order to do that and kind of map it out. I guess I'm a chemist, so I always think back to a periodic table, being able to look at trends and so on. But this was it was a global project. There were hundreds of different labs, all joining this consortium, this large project, looking at organ-specific data, looking at different techniques in order to map out the human cell atlas. And so I'm going to talk from a metadata perspective. I was involved in helping to build the data coordination platform that was really looking at standardizing a lot of the data that was coming out of this, all the sequencing labs. So I think my lesson, as it were, as we set off to do this, is that you've got 2 quite different groups of users in your community when you're a repository, and you need to choose who you're going to make happy and who you choose to make less happy, and sort of really carefully consider that position. So we have on our left-hand side, we have our data contributors, and their aim is to submit the data in order to publish results in a sort of a typical submitter or contributor fashion. They've obviously got all their metadata in a format that makes sense to them and supports their results in a way that they then want to publish. On the right-hand side, we have our data consumer, who wants to use or reuse a lot of those data sets and usually combine them with different data sets from different areas in order to do some new analysis. And so ideally, in a dream world, they would have data that was standardized and easy to consume. There was, standard ontologies and that use was already done for them. I've got sort of, I guess, along the bottom axis here, the position that a repository may take in terms of where the standard sits, and we kind of, I guess, have this imaginary effort of who has to do the work. So ENA, NCBI, that's the sort of INSDC databases, which are an archive. They're a long-standing record of sequence data, have a fairly low metadata standard, so it's easy to contribute data in. But then when you come to reuse it again, it's quite hard. You have to do quite a lot of that data cleaning yourself. When we came to consider for that Human Cell Atlas project where we wanted this to sit, we did the classic situation of, oh look, we've got all these standards, oh none of them quite meet, we need another one. And the aim was not really to make another competing standard, but in many ways that is actually kind of what happened. And so we chose a quite high metadata standard, which meant our contributors really needed to do a lot of work in order to bring their data in. And I guess the point in the middle is when no one's happy. That's a really awkward state where you don't really have enough metadata to reuse it easily, but you've still made the data contributor do quite a lot of work. So we tried to reduce the burden a little bit in terms of what we could do to support with bioinformaticians to really help with some of that metadata from the data contributor side to really try and lower that burden. And I guess that we feel at the time, and this is an old slide now, but that trade-off was worth it because you could do some really awesome things with it in terms of building those atlases and really working out what the different cell types were within the different organs. So a quick acknowledgement to funding and of course a huge team that were really behind the project. I was just a little part of it. I'm now going to switch context completely and move back to I guess, move from the UK to New Zealand. And talk a little bit about the Aotearoa Genomic Data Repository, which is a repository for non-human species in a New Zealand context, and is a project I've been involved with in the last 3 years or so. A couple of the other members, Libby Liggins and Mick Black, are here as well and presented yesterday on this project. So again, I'm going to just stick to metadata. When considering this, I think within the Aotearoa New Zealand context, it's really important to acknowledge Te Tiriti. So this is the Treaty of Waitangi, and it's a treaty that was signed between the Crown and over 500 chiefs from Maori chiefs in 1840. And so this, I guess, provides legal standing for taonga, for treasured species and objects, to have sort of legal precedence for Maori guardianship within the context of New Zealand. And so this extends to sort of DNA sequence data, both in terms of the sample and the actual sequencing. So this is the awesome team who actually deliver this project, and I guess again, and the common thread here, we did this. We invented another standard, and I think with metadata it's really tricky not to do this, and I still haven't learned how you don't do this, but I just want to talk a little bit around the why. So our aim with our schema, really, we adopted sort of the mix of 6, the minimum information for any sequence standard. We used Darwin Core, we used Geome, but actually there was quite a lot of metadata that was, quite a lot of metadata we felt we needed that was not covered in these standards. And this particularly kind of fitted in with the Indigenous governance aspect and what from a provenance perspective and a governance perspective needed to be included. We've had a couple of iterations and a couple of goes of our schema, and this is our newer one, which both allows for a lot more kind of complex experiment types that are sort of, technology changes over the last 4 years, so we've managed to, include lots of other sort of different experiment designs, but really we've been adapting the schema to allow for different types of Indigenous governance, and that includes the sort of local context, Indigenous traditional knowledge labels and notices. So I think that's really all I want to say. I'm happy to, I love a metadata schema, so I'm happy to dive into the specifics if anyone's interested. But really, I guess I'll just finish by saying that we are hosting, it's a bit of an advertisement meal really, the Genomic Standards Consortium meeting in New Zealand next year. and really pushing that theme of genomic standards in an Indigenous context. So we're looking for input from communities and experts sort of in all these spaces if they're keen to contribute to that conversation and really developing how, within the context of the genomic standards, how we can include that provenance and that Indigenous metadata. All right, that's me, hopefully. Brilliant. So I get to introduce our next speaker. Oh, thank you. Awesome. So I'll welcome to the stage Cyrus Walther to talk to us about what do we do with all the data. Thank you.
Let's see. That thing works good. The pointer also works?
The pointer works, yes.
Does it point? It doesn't point, okay. Ah, it's a very small red dot, okay. Yes, so we're switching fields completely away from what Claire has told us already towards physics. And physics is, generally speaking, a community that is well known to produce a lot of data. And the question for a lot of us as physicists, not us koalas, but us physicists, is what do we do with all the data? And the first question we have to answer about this is, what does all the data even mean? So this is a beautiful picture. All of you can think about and guess what it is. Half of you will probably know that picture by heart already. So that's the CERN data center. It's a very impressive place. Walk through that if you have a chance of being in Geneva. And what's the issue is that large-scale physics experiments are producing large, massive amounts of data. So the question is, what does massive mean? Because to some of us, massive is 800 gigabyte. To us, LHC Run 3 is 600 petabytes of data, so around 20,000 years of HD movies. No one of us will live that long to see all of that movies. I don't think there's enough movies that exist for that length. The issue is, some of you might also thank you for the radio music. Is there any chance we can get the radio music off towards the IT back there? Okay, IT doesn't seem to care. Actually, they're not. Okay, back to the topic. The point is, this is really filtered data already. So this is not the raw stuff. Raw stuff is worse. Raw stuff is much worse. So the ATLAS experiment, which is 1 out of 4 experiments at LHC, is doing this number of bytes, which translates to roughly 1 petabyte of data per second in run 1. That was the least extensive data run. They do the 1 petabyte per second. So every second we're speaking, and it's back then, 5 years ago, was doing 1 petabyte of data. Just on the run, just on the side, like 1 petabyte, 1 petabyte, 1 petabyte, 1 petabyte. That's a lot of data. And all of us were like, how are we going to manage that data ever? So the first thing we do is we do triggers and we throw away most of the data, so we get to some kind of reasonable numbers of like 600 petabytes that we have to store after like a couple of years of run 3, but most of it's going to go away. So that's what we mean with all the data. All the data is 1 petabyte per second. If you have something that does more than that, we can discuss that later after the session. I would love to hear who has the longest stack of data in 1 second. But there's not only CERN. So then I could just call my slides, why does CERN have so much data? But it's not only CERN. There's more. There are other experiments, especially also in astrophysics, that have equal amounts of data. So SKO has around 700 petabytes of data, which is also not too bad in comparison to what CERN has in run 3. So let's talk about who are these people that have so much data and why do they have so much data? So there's a couple of these things, and I just brought up a couple of logos. If your favorite logo is not amongst them, you can decapitate me for that later. We have things like the MAGIC telescopes on La Palma. We have LIGO, which are the ones that discovered the gravitational waves kind of stuff, if you remember the Nobel Prize a couple of years ago. We have IceCube, which is at the South Pole, as the name suggests, in the ice. We have CTAO, which is the larger version of MAGIC, just a little bit bigger, and we're building it. SKO is the sister experiment to CTAO, so in the same field, also an astrophysics experiment, but on a different wavelength. And then there's, of course, CERN being the mothership of all data acquisition, if you want to say so. So all of these people, that's just like a handful, like maybe like 1/5 of the number of experiments that produce a lot of data, are cases where you have these issues. So this is a very broad issue. What do we do with all the data? And the first point is, why do we need so much data? It's very easy. Most of the issues that we have in physics and in a variety of other subjects just require very complex, very large infrastructure that needs to be put together by many, many different institutes. There have to be many countries who put together funding to build one of these experiments. No one of us is going to be able to convince their government to only fund alone one of these beautiful experiments. They're way too costly. They're not going to happen. And that's the first issue. We have to come together to throw in money together so we build something that's big enough. And as soon as you have to have so many people to throw stuff together to build something so big, then you know that's also going to produce a lot of data. Second is, what do they do? It's quite easy, but it's a very broad field of people here. But they gather expertise and resources to design and build and maintain that infrastructure. So the data just comes out as the end product, but that's not what the large-scale infrastructures are for, the large-scale collaborations. And what's the effect? The large facilities enable us to do the collection of big data, which then answers the question of our universe. That's basically what we want to do. But without these large-scale facilities built by these large-scale infrastructures and communities, it's not going to work to discover anything new in our field of physics. So we need this. This is essential for us. So these big data amounts are coming out of a necessity to discover parts of our universe. But there are a couple of issues with that, and you know most of them. It's like saving all the data is not feasible. 1 petabyte per second, since I'm talking, it has already been 200, 300 petabytes of data. Triggering is interesting, but it's really hardly depending on what you find is interesting. So you're triggering on what is interesting to you. To some of them, this is a specific kind of signature. But for others, it might be something completely different. So triggering is highly subjective to the person you are and the field of physics you find interesting. Accessibility of data is very limited. If you have a petabyte per second, how do you make that available to people? No one can download that. My line at home is not big enough to download a petabyte of data or to save it anywhere. Compression of data is by analysis impacting its utility. So even if I compress that down to go to higher analysis levels, you lose a lot of the utility of the data. It's mainly not usable for most physics cases anymore, except for your analysis line. And the further you go down, the less use cases you have for that data set, which is very different from social sciences. There you take a data set and you can use it for many purposes. In physics, you have one purpose and you take a data set. And then you have that data set and then it's done, most of the time. Sometimes you can wiggle around a little bit, but not much. And then, of course, there's a lack of metadata in physics that just leads to the loss of all value of the data. As soon as the metadata is lost somewhere in the compression and is laying on some server somewhere and you don't have it to the data anymore, it's useless anyways. There's a couple more. You don't have to talk about like more reasons. It's just already enough to show that there's a big issue with this. And let's go through some approaches to show that there is some hope, and physics is actually approaching some of these matters with some interesting approaches to find solutions, because we want to find out new things about the universe. So first thing is very obvious, is the CERN Worldwide Computing Grid, which is decentralizing infrastructure. No one can build a data center big enough to store everything that CERN wants to store and produce and to work on everything that CERN wants to work on. So they have this structure of data centers, with the biggest one locally at CERN, which is really something you should see, I'm telling you. And then with a tier system ranked, a couple of other places that can join in, and everybody who is fulfilling specific criteria can join in with their computing cluster into CERN's Worldwide Computing Grid, and can have their data run on their like CERN's data run on their computing grid whenever there's capacity free. So you can include your resources. This is the only way they're able to even process all the data anywhere remotely to the size of what they have. And this tier system gives the ability to also places that are very far away from these really big data centers, and allows places that are in more remote areas where data centers are smaller to be included with the resources and really be part of the bigger picture. And with that also comes the advance on a variety of other software matters that are developed for the Worldwide Computing Grid as well. Yes, let's move on. There's another case which is not so well known, which is more in the astrophysics community, which goes in the direction of sustainability of this data. So how do you ensure that when you process the data up, no one else can use it except you for your specific use case? So how do you ensure that this is broader for more people? And what MAGIC does, it developed the AutoMagic database. At least physicists are good with naming their experiments. And the idea is that what they do is they have a really big database built up, and this database automatically picks out the criteria you need for your specific data analysis with one specific data storage. It will go to that server, do the analysis by a wrapper around the program, get you the data, process the data on the server, get it out for the next step, retrieve the respective information from the analyzed data set automatically, create a new configuration for the new data set, put it in, so automatically, step by step, provide you all the analysis steps with coming out of one configuration file, one configuration information. So all of your data pipeline, up to a certain step, basically automatized in exactly that field by having a very smart loop around submitting jobs and learning about what information is there to produce what files at what point. That way, even if you have to redo the whole analysis chain, it can be much, much, much faster than you think it might be in just completely ignoring the fact that you have to do this data analysis step by step, but you can really focus on the physics or the science you want to do, in that case, astrophysics. And what it really does, it ensures automatically that all the metadata is included. So you have afterwards this one configuration file, and whoever wants to reproduce exactly what you do, you just have to give them that specific configuration file, which is not normal in astroparticle physics. Otherwise, it's normally a complex chain of parameters you have to give on from A to B. This tool now enables people to just automatically give on that one specific file, and that config file can rerun the whole analysis. Then there's a third example, which is a little bit more complex, and it goes towards unified data formats, which is the fact that just because your experiment did something doesn't mean someone else from another experiment can implement that data if it would be open. The idea is to produce something called data level 3, which sounds very cryptical, but let me introduce you to that in a second. So the idea is interoperability between the experiments is highly difficult and highly contested to even assume this is possible. But in order to get new physics results, you want to combine the results from different experiments. You want to get more insights. You cannot get more insights if people just refuse you to have the data interoperable, actively, refusing against concepts of the fair principles. So what you do, yeah, that's just what I said. So you need processing tools that are unanimous for all of the collaborations to get you to a certain data level so you can make the files interoperable. This is exactly what the data level 3 does and what the GIDF data levels do. They provide a sustainable approach to agreeing on standards for a certain point in astroparticle physics to tell you this is the level of data with this information you have to have. And if you have this, you can take whatever experiment you have, this specific information, and you plug it into your analysis later. You can use that data. You can have much more ability for scientific discovery because you have suddenly much more information from all the other experiments. That's 3 approaches on how we're trying to tackle these massive data volumes on different sides. One being standards, the other one being sustainability, and the first one just being pure massive amounts of resources. So I also brought you some beautiful pictures because I can't let that be. You know, this is kind of the stuff that we're working with. So if you want to switch fields after seeing these pictures, talk to me afterwards. Highly recommend. And this is a little bit of what I want to show with the data levels. So this is how complex it looks. So in the beginning, you have these vault curves. So it's just nothing else but the vault of a pixel, like the camera pixel. Then later on, you have a camera image. Later on, then you have the information of whatever you want to measure, like where did whatever you measured come from, how much energy did it have, and then at some point you end up at this part, which is basically nothing else but a table of time, direction, energy of what you've measured. And this is a very, very new development towards something that people need to understand in high energy physics, that these kind of concepts and structures are important to enable discovery. We have one specific elephant in the room, and I already mentioned that. This is the elephant in the room. It's open data. Big scientific collaborations, like in physics, they don't have the data open, and they don't want the data to be open. Some of them have the data open, but for example, Magic and Hess and a lot of these other experiments, IceCube, they don't have the data open. Try to get IceCube data. It's hella difficult. Don't do that. It's really bad investment of time. You're not going to get it. So what's the issue? The issue is to get into these large collaborations, you need to pay a hefty membership fee. You cannot pay that hefty membership fee if you come from a country that doesn't have resources. To get into these collaborations, the membership fee is like, they're normally paid by the specific institutions wanting to get in, being multiple thousands of dollars. If you accept it, then you might get access to the data. Otherwise, you're not getting access to the data. And try to reason to whoever's coordinating your budget that you want to spend 10,000 bucks on one specific data set that you might use once or might not use at all because it's super difficult to operate in the first place. Hard point to make. So the FAIR principles are slowly starting to come in, and some of the experiments are starting to publish small amounts of their data open. The issue is they have to be processed up to a certain level because the tools are not open. So all of these steps that you are all used to, all of these open tools, fair data, care data, all of these measures are stuff that we need to implement. Care data is not so much involved with us because most of the time the experimental sites that we have don't have the specific issue of being on grounds of people that we want to acknowledge specifically, and those who are, there we do. Generally speaking, open data has to develop in many of these fields. So right now, there are brilliant technical solutions, and if you're looking for technical solutions to solve your issues with data science, come to the physicists, talk to us, let me know. If you want to talk about open data, please teach us. And this is a little bit where I want to grab some of the attention to say something about that there are some solutions. So CERN has an open data portal. You can get a lot of open data from CERN. Other experiments don't. Magic is trying that because the next generation CTAO will be an open observatory. So they're trying to open that up to everybody, which is a completely new concept of funding. And it has its own issues, but we're trying to get there. We're not completely ignorant of the issue, but we're trying to get there. And that's what I wanted to take you home with. So a couple of summaries to wrap that up is large-scale multinational collaborations are absolutely crucial to advance science. Otherwise, it doesn't work. We need them. But they do produce a lot of data, and this data cannot be stored. It's just too big volumes. Remember, 1 petabyte per second, every second. And at the same time, there are methods that are really sophisticated in the software and the technical regime that you want to look at, that you should look into your fields, whether they are adaptable in your fields because they're technically significantly advanced in comparison to many other fields. And they develop the software that ensures interoperability, reusability at some point with the multinational collaborations, but they're not fair and they're not open, but we're working on it. So when you see physicists, teach them about open data and fair data. If you see physicists, talk to them about the technology, I like it. And they might have something to show you. Thank you. And now I'm happy to introduce the next speaker, who's Adrianna. And Adrianna is coming up on stage, and she's going to introduce herself a little bit further in.
Thank you very much. Okay, let's try. Yeah. Thank you so much, Cyrus. Hi, everyone. Thank you for the opportunity to be here today. My name is Adrianna, and I am a PhD student. I'm finishing at the end of this month here at the Queensland University of Technology in the Center for Data Science, and I used to be the project lead of this project, Project AIMS, AI Against Modern Slavery, as part of MILA, the Quebec Institute of AI based in Canada. So being at the end of this journey, I'm really excited to have the opportunity to tell you all about the work that we've done. And importantly today, what I would like to emphasize is, while we've learned from Cyrus the challenges that they're facing when they have too much data, today I'm going to tell you the challenges we're facing when data is very scarce, but also the work is really urgent. And that's the case in the fight against modern slavery. As I'm worried that you might not be able to see me due to my height, I might move here so you can see me fully. So before I commence, I would like to start by providing a bit more background on the topic that we're addressing today, and that's the issue of modern slavery.
Modern slavery is a situation of exploitation that a person cannot refuse or leave due to threats, coercions, or abuse of power. It can take many forms across the globe, from child labor, forced labor, domestic servitude, sex trafficking, the use of children as soldiers, the trafficking of people for organs harvesting, debt bondage, forced marriage, etc. And these different forms that modern slavery is taking across the globe showcase that the statistics are appalling. There is an estimate of over 50 million people being in one form of modern slavery across the globe, and this is a 10 million increase since the last estimate of 2018. So what it means is that even though we already are doing really good work at trying to tackle and prevent modern slavery, we're really falling behind to the speed that this crime is evolving. So we need better solutions to move ahead and to start eliminating this crime. And we believe that data and AI can really play a role in helping us scale this work when it's done right and when it's made open. So to continue, when we think about modern slavery, many times we say, well, certainly this is just something that happens over there. So it won't happen here in Australia or in Canada, but it does. It happens onshore. There are estimated that over 40,000 people are in a situation of modern slavery here in Australia. But more importantly, we are all possibly connected to this crime, to the products and services we're consuming. We have estimates that the products and services most at risk of being imported, that are at risk of being developed with modern slavery, are electronic, fish, garments, solar panel, and textiles. So the clothes from our back, the technology we're using in this conference, they are at risk of being somewhere produced in the supply chain with people enslaved. So how do we try to address this crime? Well, to be able to know exactly if a product that we are buying or a service we're consuming is at risk, we need transparency. And there are already international framework on how businesses can look in their supply chain and create transparency in their supply chain that are already set at the UN level. And those type of frameworks are then embedded in legislation. In 2015, the UK government has passed the first Modern Slavery Act, asking really large corporations to look in their supply chain and to assess the risk of slavery, take action against it, measure their effectiveness of these actions, and then report back. And then in 2018, Australia passes the same law. Last year, Canada passes their own modern slavery statement. So we have already so many different legislations that are asking large corporations to do the right thing to address modern slavery or other human rights and environmental concerns at large. And all of those laws have this thing in common, which is a reporting requirement. And businesses are doing the right thing. They are writing their reports, they're publishing these reports, and then each year we have thousands of reports that rest unanalyzed because no government or NGO have the capacity to go through thousands of reports and analyze them in the depth, at the depth level that we need to be able to improve policy or take action. And this is why we think that AI can help. It can help us create a faster and more scalable solution to create a more rigorous evaluation of compliance. Of course, that will help us create accountability and transparency, and more importantly, to create a more robust climate of business and human rights. And that was the philosophy behind this project, Project AIMS, that was launched in 2019. And this project has two different phases. In the first phase, we looked at the UK Modern Slavery Act, because the law was in place for longer, we had enough documents. And then in the second place, we looked at the Australian Modern Slavery Act. So what I will do in the next maybe 10 to 15 minutes, I'm going to try to collect the learnings from this project and also to present why we think data repositories are so important and why thinking about how these laws are producing data and the data infrastructure that is needed to be able to enforce this law needs to be open and needs to be accessible to all different stakeholders. So in the first phase of the project, the UK assessment, we thought this is even back in 2019 with, okay, there are a lot of models, we're going to just take the statements, assess them with some AI, and that's it, easy fix. And we made everything open source, and we have publications, and what we're mainly telling is that, well, that's the intention we went with. What we had at the end were a lot of learnings and challenges that we faced that really helped us with the second phase. But the main challenges that we encounter when we try to bring data science in an environment where policymakers or governments are not that literate or that used to think about the data is that this resulted in a lot of challenges. So the first challenge was about data access. This legislation, the UK legislation in particular, it just required a company to publish one statement that is signed on their website that can even say we don't do anything about slavery, but this is our Modern Slavery Act, and that was still fine. However, the government also didn't publish a list of companies that were in the scope of the legislation each year. So what that means for us as data analysts is that we didn't know what data we needed to analyze. So we needed to figure out what data we needed to collect. Then, in the absence of a registry where all these documents are, we needed to go to each company's website, scrub their website, try to find the statement, then create our own repository. So we're losing a lot of data just by having this hurdle. Then, when we access the documents, we realize that most of those documents come in PDF formats. And that was an issue in 2019, it's still an issue today. A lot of documents are scanned, but not fully scanned, maybe just the last page that has a signature. So we are trying to figure out how to access all that information correctly, but also a lot of companies like to create these really complex PDFs with infographics and pictures that even the best AI today is still not fully able to understand completely, let alone in 2019. So once again, a lot of the information and a lot of data was missed because the data format was inconsistent. The third issue for us was that we were hoping to leverage open repository of data instead of us building our own annotated data set. So we went to Wikirate, the largest repository or environmental social government ESG data in the world, and they have a bunch of documents that they have assessed. So we said, just give us your data and we're just gonna teach an AI to replicate your analysis. But because the NGOs, again, when they're running their assessment, they're not thinking about how this data is going to be used further down the line by AI. This data was very messy, and it had lots of noise in it. For instance, a volunteer assessing a document can say, instead of just saying, this is the sentence that confirms that the document is approved by the board, they will add their own words saying, I think I see on page 4 that this document is approved. And all of that is noise that was really affecting the quality of the product and AI's artifacts that we were able to produce. And finally, trying to build any data project or AI project without a clear user in mind is very difficult. Because in the UK, this law was passed with the idea that consumers are going to be the ones that are going to find these documents, review them, and then decide if they're going to buy the coffee or the t-shirt that they want to buy from that company. That means that the Home Office, who is in charge of this law, didn't have an obligation to review those documents, therefore no interest really to try to think about building AI solutions in this sense. So having a clear user we find as being very important in the data pipeline as well. We collect all these learnings, we transform them in recommendations for policymakers to ensure that they publish an up-to-date list of all the companies that are in scope of the law, that they have a central registry where all the documents are being published and that those documents are being published in machine-readable formats. And of course, we encourage companies to support the policymakers in implementing these recommendations. And with that, we thought, okay, we've learned a lot, but we really think there is still a lot that can be done here if we're doing it right and we build upon our learnings. And this is when the second phase of the project started 4 years ago. And this became a collaboration between Mila and the Queensland University of Technology. But importantly for us, now we had a potential user in mind because we decided to focus only on the Australian Modern Slavery Act. And here we could work really closely with the Attorney General's Department, who is in charge of supervising this law, and therefore potentially thinking about them as users, still having Wikirate as also potential users on open source platform to use our artifacts, and also working with technology providers like Task AI, who are professional data annotators, and Abby, who has a software of extracting things from PDF. So trying to correct as much as possible for some of the data limitations that we've learned in the first phase that are still relevant for the Australian context as well. So we have a series of publications that we outputted as a result of this collaboration. And I'm going to go through some of them. And tell you a little bit how data played a crucial role in developing it and why we always kept those learnings in mind throughout the development of this research. The first paper that we wrote was aims.eu, and this paper was maybe the main contribution we had with this project, because we decided to build our own annotated data set. We wanted to be really good AI, and we knew we couldn't rely on other data sources. So we go to the registry of the Australian government, download all the statements, and then we end up with about 6,000 documents that we annotated at sentence level. So we have over 800,000 sentences that we annotate. And then with that data, we were able to fine-tune large language models and compare those fine-tuned large language models with the zero-shot models, the GPTs out there that are just using prompts, and why our research is important, and I think why we were able to publish it in really important conferences like ICLR was because we showed the limitation of generative models that are underperforming heavily compared to the fine-tuned models. They're just simply unable to understand the language that is crafted by very clever lawyers and marketing specialists that are putting those documents out there. So those models need a little bit more work and teaching in order to be able to perform such an important task. Then, thinking about our user, we knew that while this work can potentially be used by the Australian government, we also have other governments out there with the same issue. So we asked the question, can the models that we fine-tune on this data set be able to assess documents from UK and Canada? So we create more annotations. We annotate documents from UK and Canada based on the similarities between the two worlds, and we showcase that our best performing fine-tuned model is really good at transferring knowledge and being able to assess documents from the other jurisdictions, and is still performing a lot better than the zero-shot model, even with improved prompts and state-of-the-art techniques at that time. And why is this important? It means that the UK and Canadian government, they don't need to spend 1.5 years annotating data set to get a model that can help them assess their own statements and enforce their law. And most importantly for us is that when we think about our user, we always think about human in the loop. We would never argue that AI should be a fully automated pipeline that a government or an NGO will use to assess the documents. So we think about how a user, an analyst from the government, would be able to interpret the results of our AI. So we take a document, we run it through our AI, we have the sentence level classification if the company is describing or not the mandatory criteria of the law, but because this is a fine-tuned model, we needed to help the analyst understand why each sentence is predicted the way it is by the model. So we include some techniques in here, and we want to emphasize that this work will help the analyst make the final decision rather than focusing on the AI prediction as a final number, and that's it. Furthermore, in a follow-up publication, trying to improve the quality of our model, we try many, many techniques. And then we realize that if we have 4 different huge models running in parallel, trying to assess a document, there is no government or NGO that will have the resources to, and the compute power to run that across thousands of documents each year. So we take all these learnings from these teacher models and distill them in a student model, and we showcase that we can reach same performance or even better with our student model, but 7 to 8 times faster and saving up to 6% of the energy. And again, the reason why we did this is because we know that our user is in very resource-constrained environments, and we need to provide tools that will be able to be actually deployed and used, and not just have a beautiful publication that will not end up being used afterwards. Furthermore, the work so far, these technical papers, really focus on the capabilities of AI and really checking, is a document compliant or not with the requirements of the law? But we look at the literature and we say, who has ever assessed these documents? Who is interested in what companies are saying? And there's the academia, and there are the non-for-profits, the civic society organizations. So we ask, okay, so what are they asking when they're assessing a corporate statement beyond the compliance questions? So we look at the literature, we look at all the studies that have ever assessed a modern slavery statement from Australia, UK, and Canada. We map all the different metrics that they're asking, and we map those back to the mandatory criteria of the law. The reason why we do this is because we want to ensure that this research is something that would allow not only the government to check for compliance with the law, but would also allow to check for the quality of reporting, which is the important question that the non-for-profit and academia is asking. It's not only if the company is doing a ticking boxing exercise to meet the requirements of the law, but are they actually doing the important work that is needed to address modern slavery in their supply chain? So now we have about 200 questions that a user can use to interrogate this statement, and we have an entire pipeline using a mix of our fine-tuned models and other large language models and some watchdog RAG models that would allow the human reviewer at the end not only to have the ability to ask those more granular questions and check for the quality of the modern slavery statement, but also have that explainability so when they get the outputs, they understand why the model predicted what they did, what is the reasoning behind that, because many times multiple AI models reach the right answer but feel completely wrong reasoning, and therefore it's not useful. So the human is always the one at the end that makes all the final decision. So our work now is not only able to be used by governments, but also by civic society and academia. But coming back to the beginning when I was showing the regulatory landscape, so far we are addressing the modern slavery legislation. But we don't want the companies only to look at modern slavery alone, because this is a complex crime that doesn't happen in silos. We care about the human rights and environmental due diligence of the companies. So we said, what did we learn through this process, and how can other legislations that are requiring companies to report on these important issues can learn from this and be able to think about data and AI in order for them to use it to enforce these laws and act upon them. So we have this final paper. Again, we look at every challenge that has to do with data collection. We create recommendation for governments, and we explain why this is important for AI. And we do this, as I mentioned, looking at the data collection, data analysis, and the user. And finally, we map all these different laws that are already enforced, and we create an index of how ready these laws are to have AI or data science applied in their enforcement process. And we see that a lot of those laws are not really there yet. There are still a lot of things that the government needs to change to create the right infrastructure for data to help them in this process. So if they're passing these laws, they need to think about how these laws are going to be enforced. And we live in a data age, and we have the right techniques. It's about creating the right infrastructure to allow them to use these beautiful techniques that we develop. And all this work, again, having this interdisciplinary approach really allowed us to contribute to policy, contribute to the review of the legislation, and roundtable discussions. But then, as it came to an end, Carrie, my supervisor, who's also here, and I were thinking, well, let's celebrate. We're making all the work open source. The data, the papers, all our algorithms. Why not invite the global community to look at this work, find the limitations, and improve on them? So we organized a hackathon for the last month, and we were really excited that we got over 200 participants from 19 countries to participate in this hackathon and to try to help us improve some of the challenges that we had on data processing, on our AI models, on creating visualization and applications. So far, we only did models, so we don't have a software. So an NGO that doesn't have technical capabilities, you probably won't be able to just run even our tiny model. So ideally, there will be a user-friendly application or come up with completely blue sky innovation solutions that will advance this work. And the hackathon is now finished. We have all the results. And on Thursday, Carrie and I will host a panel session here in this room, actually, where we will talk a bit more about this work, but also we'll announce the winners. And we're going to tell you all about the nice things that people have built based on our open infrastructure, and I hope to see some of you there. And hopefully this case study that I presented today showcases how important it is to be able to use open data and to make our artifacts open, so then the others can build upon it, and we will show you how the teams that participate in the hackathon did just that. So with no further ado, I would also like to invite Louis to introduce his work. Thank you very much for your attention.
Thank you so much. It's nice to come in the middle, because then everybody will only remember the first and the last speaker. Good afternoon, colleagues. My name is Louis, as introduced, from South Africa, and I'm an environmental scientist, and like many people in my country, didn't get an opportunity in my field of study, so I ended up in a university environment, and grew in that space to do data governance and data management, which is my day-to-day job. But I didn't lose my first love, which is the environmental science and the sciences, and my research, my PhD research is really continuing on finding the nexus between climate change research and how higher education can really advance and bring more awareness to climate change related issues. Let's see how this works. Yes. So before I dive into policy and climate data or the SDGs, I want to tell you a story about a bird. And this is the Hadida ibis. For those who don't know it, it's a species that I studied in my first ecological research project in South Africa. And I tried to show you here, this species, or this bird, was traditionally found just here on the map, right at the bottom, which is the moist grassland, and some of the river corridors in South Africa are there, and mainly in the eastern and southern regions of the country. But now they've expanded westward and southward, as you can see, all the way to, oh my God, I'm still trying to get, all the way to Zimbabwe, Zambia, and some parts of Mozambique, as well as Malawi. And this has taken place even in the Western Cape, which is here, where the winter and the summer is at different times of the year compared to where they originally came from. So what caught our attention was what was happening in this space. It turns out that urbanization, of course, the lawns, the gardens, the sports fields were creating an artificial foraging zones. Irrigation mimicked the natural wet conditions they preferred, and climate change played a big role. You see, the warmer winters and altered rainfall made these new areas livable for these species. But what made this even more interesting was their adaptability, flexible diets, shifting breeding seasons, and the ability to raise multiple broods per year. In fact, if you're in Johannesburg in winter, you may even be able to catch this bird because they can't fly. They don't have the energy because it's so dry, there's not enough food, and they can't meet their daily needs. And if you go to the Western Cape, they've actually changed their breeding season from the traditional summer to the winter season to adapt to the wet. Now, this research taught me something, which is simple but powerful. Local data can reveal major ecological shifts long before global models can catch up with them. And that realization is what brings me here today. I'm just trying to navigate both sides. But we only knew that because the data existed, collected, verified, and shared locally. Now think about how many similar shifts are happening across the globe and in the South. Undocumented, unrecognized, and unaccounted for. The reality is most of the world's climate data infrastructure is concentrated in the global north. Climate models from NOAA, NASA, or the IPCC are powerful, but they are often built using data that isn't fully representative, especially for regions like the South, where I come from. Now, that's a problem. That's a big problem because climate adaptation policy and funding rely on the data we can see. When local data is missing, entire regions and their needs disappear from the map. Without localized temperature records, rainfall data, and emissions profiles, we end up making decisions based on incomplete pictures. This isn't just about scientific limitation, colleagues. It's justice. It's a justice issue. If a region doesn't appear in the data, it doesn't appear in the funding priorities. And we risk assessment. And that's why localized data isn't just technically important, but it's politically urgent. And I tried as much as possible to map out, but my Google, I tried to use Power BI, but I couldn't zoom enough so you can see how many organizations. I'm looking at just the main ones, and I've put some of the logos, and you can see we have absolutely nothing in the global South. So climate data is not just about numbers, as I've said. It guides policy, it informs disaster preparedness. It shapes how we build, how we farm, and how we live. The world relies on these repositories that I have pointed out here, including the World Banks as well. These institutions offer decades of climate records, projections, and insights. Some of them open, some of them not. But here's the issue. If all of them are based in the north, where is the representativity in the south? Right? And while satellite sensing gives us global coverage, it can't replace localized on-the-ground data, like the Hadida species data I just presented in my opening, especially in areas with complex, variable climate impacts. Even when countries in the global south collect data, it often stays siloed in institutions, like the data that I just presented, and other data that I've worked on in my master's research. It stays siloed in institutions, it isn't integrated into global repositories, and it isn't considered equally valid in international assessments. And that creates a feedback loop. Less data means less visibility, which means less funding, less policy attention, and fewer resources for resilience. Climate models from the institutions that I presented here are powerful, and they are often built using data that isn't fully representative, especially for regions in the global south. And without the localized data, as I've said, we end up making decisions based on incomplete pictures. And it's not just a scientific limitation. And I repeat, it's a matter of justice. I'm not a politician, I promise. Now, let me bring this closer to home. As I've said, my background is I'm a bureaucrat in the university environment. And universities in South Africa in particular face real energy and infrastructure challenges, from spiking electricity costs to legacy buildings that were never designed with sustainability in mind. But they're also uniquely positioned. We are very uniquely positioned because we function like small cities. If you consider all the services and all the activities that happened in a university, with all the offices, the lab, the residences, the transport, the waste, and the energy systems in all one place. That means the ideal testing grounds for climate data generation, energy efficiency strategies, and smart city innovation can really happen in a university environment. But yet, most of the valuable environmental data collected in universities stays in siloed or worse, even unused. Right. Now let's zoom out. And you have seen the depressing UN report last year and this year. I don't have to repeat how depressing that has been for many of us who've been watching what is happening. It paints a grim picture. The world is not on track. In fact, we are falling behind. Not a single SDG is on track to be achieved by 2030. Progress on goals like zero hunger, life below water, life on land, and strong institutions have stalled and even worsened and reversed. And while we have better data than ever before, the gap between knowledge and action remains quite enormous. And COVID-19, of course, just disrupted the progress. Conflicts are rising, I don't have to emphasize that enough, and climate change is accelerating. But there's another issue that underpins all of this: the inability to accurately track and measure progress in many regions, especially in the global south. We are measuring global progress with incomplete and uneven data. If the global south isn't equally represented in climate data sets, we're not just missing the picture, we are misrepresenting it. Without localized, accessible, trusted data, we are driving global development with blind spots. And this is why data equity is not just a technical issue, it's a global accountability issue. And yet, of course, there is hope. And yeah, I'm South Africans, and we really can't finish a presentation without talking about Nelson Mandela. And that's why I've got the line on my head as well. And yet, there is hope. Education is still one of our most powerful levers of change. At COP29, governments recognized this and made key commitments: embedding climate education in all levels, promoting climate literacy, advancing the Baku Initiative for Climate Resilience Education Systems, and supporting green skills development for a sustainable economy. But again, none of this can be tracked, scaled, or made effective without localized, accessible data repositories across the global south and the north alike. And at COP29, education finally got the attention it deserves. I've been watching COP since Kyoto Protocol. I think that was 1992. And COP 2019, I think it was last year, no, the year before, was the only time where education really took the center stage. And we finally got the attention it deserves, and leaders agreed without climate literate populations, we can't transition fast enough. The Baku Initiative emphasized building climate resilient education system, but here's the thing: you can't teach what you can't track. If data is still stuck in global repositories, disconnected from local realities, education becomes theoretical. Students don't see how it applies to their communities, policymakers can't plan, and educators can't evaluate the impact. This is, of course, this is where universities, especially in the South, can lead. Universities in the Global South are doing very important work, collecting environmental data, running research projects, and engaging with communities like the examples I gave earlier. But they're rarely seen as formal parts of the climate data ecosystem. And that's a missed opportunity in my view. These institutions can serve as decentralized, trusted, and context-specific data hubs. Everybody trusts academics and universities in terms of challenges. But for that to happen, we need infrastructure, incentives, and intentional partnerships that treat them as equals and not as afterthoughts. So my research shows that universities are ideal test beds for smart city innovations, and I can't wait to finish my PhD work because it really centers around this. They have the infrastructure, they have the talent, and the diversity to make change scalable and replicable. I'm almost done. I'm almost done. You're giving me that look like I should be rushing. Now I'll be done in less than 5 minutes. Now, many global data sets from the FAIR principles, as you know, have a strong foundation, but we must go further and embrace collective benefit, authority to control, and responsibility and ethics. This is about the democratization of data. It's not enough for data to be technically open. It must also be ethically governed. And the FAIR principles are foundational for open science. But if we stop there, we risk repeating colonial patterns, extracting data from the global south without shared control or benefit. Maybe I should repeat that. No, I will not. And that's why the CARE principles developed to guide indigenous data governance are essential. We need to ask who owns the data, who benefits from the data, and who decides how the data is used. Universities, especially those embedded in communities, are well placed to lead the shift from open by default to open by design and with consent. And I want to underline consent. Indigenous and community knowledge must be recognized, protected, and governed by the communities themselves. And this is not just a nice to have, but it's central to real data equity. These aren't just abstract ideals. They are achievable with the right support and the right mindset. We need to build the technical backbone for regional data repositories, but also the relational backbone, partnerships based on trust, respect, and shared ownership. And we need to change how we measure success. If we want real progress on climate change and development, the Global South must be at the table, not just as data sources, but as data leaders. If you remember anything I said, just one thing that you should remember. Data shapes decisions, and when the data is uneven, so are the outcomes. So let's recognize the untapped power of institutions in the Global South. Let's invest in localized repositories. Let's elevate regional expertise and co-create a truly global climate data ecosystem. On that, one that reflects the realities, the voices, and knowledge of all. And I thank you. Now I have the honor to present my colleague, Dr. Pragya Chaube.
Thank you so much, Louis. And just before I start, I mean, you have to give it to all my colleagues. They did a fantabulous job with Claire talking about genomics, data, Cyrus giving us idea about physics and some petabytes of data and everything, and Adrianna talking about data and social sciences, and Louis talking about the very important aspect of data in Global South. So I really want to give them a huge round of applause. And that was also because so that we all kind of wake up, you know. I have been actually struggling with, I'm sorry, I will use this instead. This is working, yeah. I've been struggling with jet lag and everything, so I just wanted to hear the round of applause. This is audible, right? Yeah, that's good. Okay, I will introduce myself. My name is Pragya Chaube. I work at UPES University, India, and my background was basically in genomics. But at some point, I decided that whatever I'm doing, it's not really making a huge impact. It's, you know, whatever is happening within a lab is not really translating to what is happening on the roads or to an average person. So I just decided I will switch. I will work on science policy. I will talk about how we can make this data useful. And that's how I got into the huge word of open science and open data and how that is actually affecting policies. But before that, I kind of realized that before we talk about policy and how data is affecting policy, there are so many things that goes happening in the background. So I'm going to talk about the very basic aspects, the very basic things. So firstly, we all have seen this page. Is it better? Oh, way better. Yeah. So we all have seen this page, but the reason I'm showing you over here is because of this particular thing. Stand on the shoulders of giants. This was written, we all must have known, this was taken from Sir Isaac Newton's letter to Robert Hooke. If I have seen further, it is by standing on the shoulders of giants. I really love this particular quote when we are talking about open data or open science or anything, because it kind of encapsulates everything that we do in science, how science is done, what it is all about. Science is incremental. It grows incrementally. That is exactly what that quote was talking about, and that is exactly why we are here. We are talking about open data, or why we should be having data repositories. Whatever we are doing is basically because of this one particular reason. And the second reason I have put this slide is because I really love this photograph. This is the first journal, not the first journal, but the first journal as we know it, as we know peer publishing and publishing today. So this is just a round of the historical context that before the 1600s, science was not as open. People were not talking about putting their data out in the open. It was all closed. They were secret, not secret, but like there were small groups where the data was being shared. And then the revolution came with the Royal Society, and this was their first journal that they came out with, and that was the idea that whatever we are doing, we should put it out in the open. And this kind of continued in the 18th and 19th century, but it kind of changed towards 20th century. Like few things happened. World wars happened. People wanted to keep their data closed. They wanted to keep it within their nations. And also, private publishers got into this entire picture. And with private publishers, we knew that a lot of things happened, Pandora's box opened, until the 21st century IT boom happened. With the IT boom, it was actually firstly the physicists who actually started putting their data and everything in the open. Cornell University started the archives, and that is where the entire journey and the entire conversation started. But the problem over there was, and the problem today still is, even when we are talking from the policy perspectives, when we are talking about open science, there are many, many verticals of open science. I mean, a lot of you must have read the UNESCO recommendation on open science that came out in 2021. One of the lesser known child in that thing has been open research data. Well, and we all must have seen that diagram, and we know that this is how UNESCO has defined open research data. It is digital and analog data, raw and processed. It should be fair and care principles. Yeah. So why should we put it out in open? I don't think we need to talk a lot about that. I mean, science is built on data, and we require it for transparency, reproducibility, reusability, to produce trust in science and collaboration. And as we knew, as there was this conversation yesterday during the plenary when they said that only fraction of data actually goes out in the open, and that actually causes a huge disservice to entire scientific community, because we are losing, according to this EU report, we are losing 10 billion each year in the academic sector alone. And there's another report that says that in 20 years, 80% of the data is already inaccessible. And we already know, like, just producing the data, getting the data, that requires a lot of funding, that requires a lot of human efforts, that requires a lot of time, that requires just a lot from us. So to address such concerns, there have been a lot of initiatives have been undertaken, like the top committee by Center for Open Science in 2014. They recommended that there should be some guidelines for journals, there should be some incentivization to practice open science by the researchers, where they can put their data out for transparency. And there have been such multiple initiatives which resulted in some progress. Yet, a 2018 report by Elsevier claimed that majority of the researchers publish their data only in supplementary information. Nobody is using public data repositories. So that was 2018. So just looking at what is happening now, what is the global trend on open data sharing? As you can see, 74% of the researchers report that they are doing this, but not through data repositories. They are using just supplemental files, which basically we know is not the entirety of the data that is required for science reproducing. And then there are a lot of researchers who claim that there's not enough institutional or technical support, and 85% of the articles as of 2022 had no link to underlying data sets. And if you think this is bad in some countries, there are countries like India, Brazil, and Ethiopia who were, that shows that they have, well below 25% repository sharing. This is one side, like who's sharing and who is not sharing, but then there is also this other side, like whether people are actually thinking about it. So this is taken from r3data.org, and as you can see, I have put numbers of the number of registries, open data repositories that are indexed on this particular database. In India, there are only 51 repositories, and compare that to USA or UK or France. The reason this is important is because when we are actually looking at these repositories, this number where the data is based, as Louis had pointed out, most of these repositories are in global north and not so much in global south. Although this number actually gives you nothing because it does not really tells you how these repositories are being used. The only thing it tells you that whether people are thinking about it. So I'm going to come back to bring the focus to India, because that is where most of my work has been. So which is the third largest research publisher, as we know, through the NSF data. But yet, it is among the, it has the lowest ranking when it comes to data adoption. And as of 2022, there were only 8.5% of Indian authors who have deposited data in repositories, and their familiarity with FAIR principles, I'm not even talking about CARE principles, but just the familiarity with FAIR principles or open science principles is severely low. And this is despite having some sort of policy backup. There was this policy, NDSAP, that came out in 2012, which talked about there should be data sharing, and then there are already draft policies, which are still in the draft phase because it's government of India, and yet, they have not become proper bills yet, but they have talked about that there should be data sharing. But as you can see, it's not happening. So to understand what is happening at the granular level, my colleague and I, Dr. Momita Kole from Indian Institute of Science, Bangalore, we decided to see what is happening at the grassroots level, and we actually went around asking people, like, what are you doing with your data? What is happening? And we took the case study from this one particular institution where we interviewed about 15 people, researchers from different disciplines across different career stages, and who are actually involved in different kinds of research. And what we learned from this particular exercise was a very keen insight into this particular Indian context, like why they are not sharing their data. Firstly, a lot of them did not see any problem with their current data sharing or archiving practices. They're like, oh, we don't have any problem. I mean, yes, we don't share our data, so we don't think about long-term preservation, but that's how it is. And when we talked about their opinion on whether it should be funded, whether it should be put out in the open, they said, like, yes, publicly funded research should be put out in the open, but it's not always useful or feasible. And yeah, they just did not want to do it, despite the fact that they felt that they should do it, but they just don't want to do it, which is the kind of contradiction that we are working with. And they did find that it will be useful for academic reuse or for other researchers, but that was their opinion. But their biggest concern on their data sharing perspective was basically around data scooping. So they were afraid that if we are actually putting out our data, it could be used. They are basically of the opinion that if we have put so much effort, we can use this data for one publication to second publication, get at least 2-3 publications out of it. But with the first publication we are putting it out, there is a higher likelihood that somebody else from the global north could actually do the data scooping, because, well, to be honest, our funding procedures are quite slow. So that was a major concern. And then there were also other concerns regarding raw data can be manipulated. And some people were just really, really struggling with technical and infrastructural constraints, people who are working with big data. So that is a huge problem still in the global south, in India. So following this, I cannot show you that we did actually a lot of follow-up with the ECRs as well, and that was a UNESCO project, but it went into an internal report. We asked about 200 ECRs on what they are doing with their data and how they are using it. And again, when we talked about open research data practices and their familiarity with FAIR, they absolutely did not know anything about it, but they were willing to use open research data repositories like Zenoro and Figshare, because the point that came out, like, it will help us a lot with data storage practices, because currently a lot of it is coming from their own funding. So there was a lot of enthusiasm among ECRs on this, and about 80% of them actually wanted to learn a lot about this particular practice, how to do open data practices. So with UNESCO New Delhi, UNESCO Beijing, and UNESCO Jakarta, we actually created Open Science Workshop webinar series, just talking to ECRs from India, actually, that how they can use the existing infrastructure for open data practices. And we also conducted workshops, and we have been conducting workshops basically based on this particular topic, trying to do our best, trying to raise awareness on this. But obviously, this is just one aspect of it. Our learning has been that despite their policy efforts, just because the awareness is quite low, and there has been a lot of cultural and disciplinary differences, people are not very open to sharing their data. And of course, we are doing our bit through a promotion of open science culture, but we are actually also hoping that there could be some mandates from the journals, especially as journals and the funding agency, that could change this behavior. And obviously, we need some incentives like citations or some disciplinary norms that could actually help with this. But yes. But again, I do not know. I mean, it's a long journey, and we do not know whether people would be as open about data sharing. I mean, to be fair, I would have liked to show you some stats over here, but due to some internal problems and something, these people were not open to sharing their data at all. So that's how it is. That is the perspective from the Indian context. And with this, I finished just in time. So thank you. Thank you, everyone. Yeah. So I would invite all my colleagues over here on this stage, and I think we have just enough time for one question. If anyone has a question for either of us or all of us, I think you can come up on the stage. Are there? Are there? Okay.
Satisfied with a lot of talking.
Well, it's already 17:30. I think people are waiting for their coffee now.
Yes, I think everybody seems satisfied. If you have questions, feel free to talk to us after the session as well. And of course, coffee is as tight as you feel like. And thank you very much again for attending and spending the time with us.
Let's take a picture.
Thank you all for coming.
Yes. Thank you. Yeah, thank you everyone for joining us today. So yeah, and we'll be very happy if somebody can take a picture. Yeah, there's no online. Can anybody help us taking a picture for us? Yes. Yeah.
That's fine, don't worry. It's fine, it's fine.
I'm not.
It's going to be fine. We have to move a little bit.
Want to sit down or stand up?
Let's see, because the lighting,
Are you sure?
the lighting is not.
It's fine. Okay.
I also wanted to suggest if you want to stand, come down so that the light does not. It's all good.
No, Cyrus and I will
Oh,
at the end.
yes, like the guys on the sides.
The gender.
Are we
Are we
crossing
doing
legs?
the?
Yes, let's cross our legs. Yes.
It's on counter.
Landscape is okay, or should I also do portrait?
Everything's fine.
Whatever you can.
Thank you so much.
Merci beaucoup.
Okay, good. Coffee.
Have a nice evening.
Thank you, you too. Enjoy.
At least I turned it off before I dropped it. Yeah, no, we didn't invite her into the group chat. Because it was mostly for the other session.
Yes, you have.
Yeah, you're right.
Yeah, we can.
That's something we can change, generally speaking. No, I'm not living in Geneva. I just visit that frequently for a variety of reasons. Given the fact that I've been in for like 4 years in certain collaboration and then left, I'm not at CERN so much anymore, but I have been and I still have good friends there. But generally speaking, our telescopes are in La Palma, so the nice picture I showed is like one of them was from me, the other one was from my colleague who has a proper camera, which I don't. It's pretty nice.
When I was still a student, I always had this dream job of teaching at the UN Institute.
Oh, you want to get the UN? Yeah, but we can arrange that.
Oh,
Finish your PhD, we can arrange that. No. I know who to ask. I know who we can set this up. No worries.
That has always been my dream.
I know who to ask. I know who can get you in there. Probably first you have to do an internship, and after you have done an internship and you prove yourself, because they will not hire you if they have never seen you and they don't know how you work, and then they will fix you for some kind of project, or you get at least an affiliation with them, and then you can figure. I will put the person together who you should talk to about this. But the question is, are you going to take respective people with you to Geneva then? Just do it. Okay.
But you need to leave either in the French side or the Italian side, so you have the
Geneva on the
salary
French side
from
is fine.
Geneva, but you pay rent and all of this in French.
Ah,
And you're
this is-
like one bus from CERN.
Yes,
Like, it's
one was
really
from CERN, and I will let
my
you know
God.
there are contacts at CERN who can tell you how to rent a place that will not make you broke and have you sell your kidney.
Yeah. Yep.
That sounds important.
It is very important, let me tell you. Rent in Geneva can be like 8,000 Swiss francs or so. Yeah,
I said no, I